your review for the first half. Uh, for Learning Target 1 and 3, we're taking a look at a group of 78 third graders in elementary school who took something called a self-concept test that measures how they feel about themselves. Higher scores indicate more positive self-concepts. So we've got this histogram right here that describes that, and then we also have a statistics summary here giving us the number 78, the mean 56.85, the standard deviation 12.35. Those would be the key things that we're looking at, and of course we have minimum, median, maximum in the first and third quartiles. So Learning Target 1, it says that 33 students had self-concept scores that were higher than 62. So if Kennedy has a self-concept score of 62, calculate the percentile. Well, remember that percentile is lower than. And so if we took the 78 students and then we subtracted out the 33 that were higher, we would get the ones that were lower, but of course we also can't include Kennedy's score. We're not just purely lower than Kennedy, so we subtract her score as well, and that would leave us with 44. There were 44 that were lower than Kennedy's score, and so remember percentile is the number that were lower divided by the total, which in this case gives us 0.56, in other words, 56th percentile. And what does that mean? Well, it means that Kennedy scores higher than 56% of the other students. Learning Target 3 is about finding z-score, and remember the reason why we find z-score is so that we can compare it to somebody that has maybe a different total number. If it's got a different total number, then it would be a little bit harder to compare. And so here with the z-score, remember it's the individual score minus the mean divided by the standard deviation. And so when we do that, we get 0.42, which means Kennedy is 0.42 standard deviations above the mean. If of course, the mean is 0. All right, Learning Target 2 and 4, we're using this cumulative relative frequency graph. And we're talking about songs in minutes. And so Learning Target 2, interpreting median and interquartile range of song lengths. So what we're going to do is we're going to draw lines on our graph to show that. And well, the 25th, I guess the median would be the 50th percentile. So that 50th would be 0.5 right here in between 0.4 and 0.6. So we draw our line over to the graph, we go straight down, and it looks like it's right before 4. So I approximated about 3.8. The interquartile range, of course, something that we learned in Chapter 1, would be the third quartile minus the first quartile. The third quartile is 75th percentile, so 70% would be right here in the middle, so 75% would be another halfway to 0.8. So again, we go over and then we drop straight down. Looks like it's about maybe a little less than 5, so I guessed 4.7. And then the 25th percentile, 2 and 4 is right here, so 30th would be in between, so it'd be another halfway in between. So 25th percentile is right about here. We go over it, we drop straight down. It looks like it's maybe 3.3. So subtracting these two things, I'm getting about 1.4, but of course we're just approximating, so we have a small range that we could be in that would be acceptable. Okay, looking at Learning Target 4. We're taking a look at the mean song length was 4.23. The standard deviation is 1.38. And so we want to create a mix, but we want to have 5 seconds in between songs. We're going to add 5 seconds to each song. We also want to express this time in seconds rather than minutes. So what does this mean? What is going to happen to the mean and the standard deviation? Well, if we're going to add 5 seconds to the mean, would that affect the mean? Or I guess we're going to add 5 seconds to each song. Would that affect the mean? And of course it would. Every song would go up 5 seconds. But if we're converting this to seconds, which we probably want to do first, then we would multiply every number by 60, and is that going to increase the mean? And of course, yeah, the mean would, everything would go up 60 seconds, so the mean would go up 60 seconds. If I add 5 to everything, then yes, the mean would also go up 5. And so both of these things affect the mean, multiplying and adding, And so multiplying gets me to 53.8, adding the 5 gets me to 58.8 seconds. However, when I look at the standard deviation, multiplying will affect the standard deviation. If everything goes up 60, the standard deviation would also go up 50. But since we're comparing this, like standard deviation is distance from the mean, well, the standard deviation is not going to change at all if I add 5 seconds because everything is still the same distance from the mean. And so I don't add 5, I just multiply by the 60 and I get 82.8 seconds. All right, learning target 5, drawing and labeling lines that estimate where the mean and median would go on this skewed distribution. So, if it was perfectly normal, the mean and the median would be right here at the very center, or the peak. Of course, because this is skewed, you realize that the mean is going to get skewed over with it. The median will also, but not necessarily as much. And so the median is not going to be perfectly here. It's skewed a little bit, but the mean is going to be skewed more. And it's not just anywhere down here. Again, it's an approximation, so there's a range, but we're looking for the balance point with the mean. The area of this should be about the same as the area of this, and so that's what we're looking for. If we put the mean way down here, this is definitely not the same as all that. So that's what we're looking for when we're looking for a spot for the mean. Learning target 6 through 8. Here we're using some data about distance runners and their weights. The mean, which would go here in the middle if it says that we are distributed normally, is 63.1, and then the standard deviation is 4.8. So the first standard deviation, second, and third, we're just adding 4.8 each time, and we're subtracting 4.8 each time to get the standard deviations that are less than the mean. For learning target 6, we can use that good old 68, 95, 99.7 rule to help us out. Finding the body weights, or the proportion of body weights, in between 48.7 and 67.9. Notice those are in between the third standard deviation to the left and the first standard deviation to the right. My shading didn't really come through, but you can see that I shaded that area. Well, on the left, and there's a couple different ways you could do this, but I chose to do it this way. On the left, you would have basically everything, the 99.7, but of course it's only on the left-hand side, and so I would divide that by 2. And so 49.85% of the data is from here in the middle out to this side, the third standard deviation. On the right, I just have to the first standard deviation, which is 68%, but again, I just want the half that's to the right, so I cut that in half, and that's 34%. So 34% is right here. So if I add this section on the left and the section on the right, I'm going to get my total, which would be 83.85. And there